Okay, so in this video we're going to be looking at a few practice questions on reactions of alkenes here. So looking at turning a few into epoxides, a lot of transformations into alcohols, and so yeah, let's take a look at the first question here. So let me go to the side a little bit so we have some room here. Okay, so what do we have? We have this compound here. Reacting with bromine, H2O, and then our sodium carbonate. And one one key thing here we're going to look at, obviously, we're going to form an alcohol in first step. Alcohol and a halide is also going to be attached. But the key thing we need to note here is the sodium carbonate reagent, which is going to form an epoxide. So let's quickly give our reaction mechanism for part one. Here, okay, so obviously I have bromine with dipoles, positive and negative. Our double bond is going to attack positive bromine, giving us this sort of resonance intermediate. I'm going to give it a dashed, because I think we still need to talk about stereochemistry here. It's this is an SN2 like reaction. We know that the water is going to attack the more substituted carbon here, so H2O is going to attack here. We almost forgot our positive charge. I'll chuck that out. It's hard to see because the pen is quite thick. And if I can, nope, this is the thinnest it goes. Okay, anyway, so it comes in here, arrow breaking that and here, and because it's SN2, we're going to have an inversion of stereochemistry, so our bromine's obviously going to be the same, but then coming off our, and really quickly we're just going to write a minus H plus here, OH like this, just to indicate that we've obviously lost the hydrogen from water to give us this alcohol. Awesome. So, and then here I'm just going to write like SN2 like reaction, therefore 100% inversion of stereochemistry. Nice. Okay. So what happens next is we get our reagent of sodium carbonate, and what really happens in this, if we consider the chair conformation of this structure here, sorry, it's not particularly great, but we have our bromine here, we have oxygen here. I'm just going to draw one of the orbitals, and And this is essentially going to move into this pair is going to move into this orbital here, and our bromine is going to become a leaving group, and this is going to form. We'll just write the reagent Na2CO3, and then this is going to form our epoxide. It's going to have this stereochemistry, like so. Lovely. So this is part A. Well, this is our initial compound A, which has the C12H16O oxygen. Here's our lovely reaction mechanism here. Wasn't really too hard, I don't think. So what do we have now? Well, this phenyl sulfur compound here, this is actually going to be a good group to expand our epoxide and turn it into an alcohol. Again, another SN2 reaction. I think it's really good to consider the base here as well. So what we also have sodium hydroxide, so I would just do something like this, add the sodium hydroxide just to form our ion here. Obviously double bond our sodium and our water, H2O, which is good. Now we have now we have an ion here, ionic compound, and then salt, and then yeah. So this is going to attack and open up the epoxide. Essentially, this is going to attack the least substituted carbon instead this time. So phenyl. And our lone pair is going to attack this carbon here, like so, breaking that one. And I'm just going to draw a plus H plus here, which we'd usually get from the water anyway, so no point in really showing that. I'm going to have an OH, and then our stereochemistry is going to change again, like so, and that should be our final compound, B. Nice one. Might just write that here, 100% inversion of stereochemistry. Now this question wasn't too hard. Part A is not too hard. It's only worth 7 marks. So not a lot of. If you know what the reagents do, then not a lot of work to go into that. However, I think part B is a little bit harder here. So with 9 marks, we only need a mechanism for one, but I'll give mechanisms for both. More than one step is required in each, so it's always good to note what. So we want to suggest reagents, more than one step is required, and we need to write mechanism for one of the transformations. So part 1, it looks like we're going to form an alcohol of some sort. So this OAC is AC is a acetyl group, so it's essentially this, right? So actually we have an ester here. Well, to go from our alkene to an ester, we could go from an alkene to an alcohol to an ester. Another thing to note in part 1 is we're actually doing anti-Markovnikov addition. Anti-Markovnikov because we've generated our primary alcohol instead of secondary. That's quite important to note. Okay, nice. So what I would suggest here is start with hydroboration. Hydroboration, because this is good at oxidizing the alkene and leads to anti-Markovnikov's rule, and then to turn the primary alcohol into our ester. We can just use an acyl chloride and a good base. So then primary alcohol to ester, we can use ACCl plus ET. Triethylamine is a very good base in this case. So we'll just give the overall. This is a very long reaction mechanism, which is why it's quite annoying. But so the reagents for hydroboration are, yes, I'm pretty sure it is THF, which is this funny looking molecule here. Then our second lot of reagents are hydrogen peroxide and a base of sodium hydroxide. And then for part 3, when we now have our alcohol, we'll use our acyl chloride and our triethylamine. And that should give this here. Now I won't give the reaction mechanism in this video, I reckon, because I've already gone over the hydroboration in the previous video. So if you need help with that, just I'll probably link the video here. But part 2 I'll definitely give reaction mechanism, because this is a bit more interesting of a question and quite hard to get, I think, as a beginner. But what we're looking at here really is forming a tertiary alcohol, and also we're extending the carbon chain length. I don't know if you can see here, but we're extending the carbon chain length, which is interesting, because if we form a carbonyl compound, and then use a Grignard reagent, we can then extend the carbon chain length whilst reducing our carbonyl compound to an alcohol, which is pretty cool. It's pretty cool. So I reckon in order to do that, we're going to have to use ozonolysis. To produce our carbonyl compound, which should, so something like this. Then we're going to need an ethyl group and so Grignard reagent. So let me just give the overall reaction here. So part 1, we're going to need ozone, essentially. Then we're going to need DMS, or dimethyl sulfate, which is going to help form our carbonyl compounds. Good nucleophile here. And then part 3, we will need our Grignard reagent. Usually this is in like a solvent, so perhaps a good solvent will be pardon me a second. Okay. So a good solvent. Okay. ET2. Okay, and this is going to form tertiary alcohol here. So let's give the reaction mechanism for this one, because this is quite long, but it's quite interesting, so it's good. First of all, let's consider what ozone looks like. We have single bonded oxygen and then a doubly bonded oxygen. So the single is going to have 3 lone pairs and of course an overall negative charge, whereas this oxygen is only going to have 1 lone pair, overall positive charge, and then we have our nice oxygen here with 2 lone pairs, no overall charge. So what's going to happen in this mechanism is let's draw our ozone out like this, I reckon. So our negative charges come in and attack here. This carbon's going to come and attack here, and this bond's going to break here. And that's going to form this sort of compound here. Okay, nice. Well, essentially, oxygen bonds are very weak. They're very weak. So what's going to happen is, still imagine the 2 lone pairs on each of these. So this oxygen bond is going to break, come in here, and so this is going to come to our carbon, and our carbon bond. Oh, pardon me a second. Shambles here. Right. So that should be carbon. That should be the oxygen, and an oxygen. That carbon's bonded to an oxygen, like so. Okay, so this oxygen bond is going to break. This lone pair and this oxygen is going to attack this carbon, and then this carbon, and it's going to break and go here. And what we form is 1 carbonyl compound, like so, 1 ketone. So like so, and we will also form our carbon like this, basic aldehyde, almost, but again, this oxygen has a positive charge, this has a negative. We'll draw it this way around. And remember, 1, 2, 3 lone pairs, 1, 2, only one here, sorry, but a positive charge. And what we need to also remember is the dipole that's present on ketone. So we have a partially negative charge here and partially positive. What actually happens here is these two compounds repel each other. They're going to repel each other and force them to move around a little bit. Like so. And what we have now is this positive charge, this partially positive charge on the carbon is actually going to attract this negative charge on the oxygen. Just drawing the lone pairs in here. And so this is going to come in and attack here. We have too many bonds on this carbon, so we're going to break one of these bonds here. And actually this will then go on to attack and attach to this carbon, breaking this bond here. And we're finally getting to the end product of the first step of ozonolysis, where we have a carbon there, oxygen, oxygen, like so. Okay, nice. Now our dimethyl sulfur step. So our sulfur is going to have 2 lone pairs attached to 2 methyl groups. And it doesn't really matter, but it's going to come in and attack this oxygen here. Which is then going to break this oxygen-oxygen bond, because remember, the oxygen-oxygen bond is very weak in comparison to the carbon-oxygen. Then this carbon-oxygen bond will break. And we'll form our alkene here. Our alkenes or our carbonyls? Our carbonyls here. Plus this. Okay, and actually this sulfur takes an oxygen, becomes DMSO. Oh. Now this here, this is the product we want, and so we're going to react it with our Grignard reagent now. Exciting stuff. Getting onto carbonyl chemistry, very fun. So very simple reaction mechanism here. We're also going to need water. I did forget about that. We'll put 4H2O just to form our alcohol at the end. Sorry, this is a very long reaction mechanism, but this is very good practice. So we have our ET, we have our Grignard reagent, magnesium bromide, and then obviously our solvent, whatever is, and then we have our water. So imagine the bond here between the ethyl group and the magnesium. It's going to come in and attack this carbon here, and we're going to have a transfer of electrons to oxygen. And we're going to form our sp3 tetrahedral intermediate, which is just quite a common intermediate. Okay, just stick a lone pair there for good measure. Why not? Actually switch. And then we have our water, like so, which is going to take a hydrogen off of here and leave us with the product we wanted. Awesome. So I just thought I'd go over a few practice questions here because of the recent videos I've been making. I haven't really put too many questions in the back at the end of those videos, so hopefully this is gonna help out a lot of work out any confusion that may have gone on in those videos.